Today we're going to take a look at section 3.2. We're looking at sum and difference formulas. What we have been doing up until now with a lot of the trig from section 1.1 on has been very specific values on the unit circle, right? And they work great. If I give you a 30-degree angle, you know what that point is at this point. We can talk about the sine value of that or any of the other trig functions and we're good to go. But if I gave you the value that's sine of 15 degrees, that is not on the unit circle. And it isn't just cut the sine value in half. We can't take the angle and cut the value of the sine in half. It doesn't work like that. So we need some additional tools in order to be able to make sense of and be able to use the other values on the unit circle in an effective way. Does that make sense? Okay, so that's going to be our goal as we move through sections 3.2, 3.3, and 3.4, is there will be a bunch, that's the other identity sheet that I gave you, of different identities that allow us to find angle values when we don't have that value on our unit circle. So let's take a look at our leading idea. The sum and difference formulas show us how to break down complex angles into simpler parts, helping us to understand something that might initially seem complicated. We trust the formulas, knowing they will simplify the problem and reveal the answer. In life, it's similar. Sometimes challenges feel overwhelming or confusing, but when we break them down and trust God's guidance, we find clarity and peace. Just as these formulas connect parts to make a whole, our faith connects us to God's bigger plan, even when we don't see it all at once. Let's pray. Dear Heavenly Father, I thank you so much that we get to come today, that we get to be here at OBU, that we get to have an opportunity to learn and to grow, and all of that is due to you, and we thank you for that. Father, I thank you that each one of these students is here this morning, that they're alert and that they are working through material and toward the goal that you have given them. Be in our class session today, please give me good examples and proper language to use, and give the students good questions to ask for clarification. We pray in Jesus' name. Amen. So we're going to start with our sum and difference identities. All of these are already written out for you, either on the sheet that I gave you or on the notes, or actually they're on both. And what they show us is, and we mentioned this before, but let me just reiterate, these angles, right, are in Greek letters. And they show us what happens when we take two angles and we add them together. Now, in particular, they will often create values that are not necessarily the ones that were on our unit circle. So we see over here, we've got angle measures showing up, right, in two different locations. Each of the angles, they alpha are in two different locations, and same for beta. And you see that there are 6 different identities here, right? So as we're taking a look at these, you need to make sure that you're looking at the right one. The signs matter, right? If I have cosine of alpha plus beta, I have a different identity than if I have cosine of alpha minus beta. The location of the sign matters. Not only that, but in some of the cases, it depends on which one we're working with, whether it's an even function or odd function, the order matters too, right? So cosine of alpha minus beta is not the same thing as cosine of beta minus alpha. We need to make sure that we pay attention and keep things in the right order. So our goal as we work in this section is to do 2 different kinds of problems, generally speaking. One is for us to be able to take angle measures, like I alluded to before, that are not familiar to us angles, and be able to turn it into something that is. And part of the reason for doing so is that it allows us to get exact answers. Because some of you are thinking, well, why? I can take my calculator and I can type in sine of 15 degrees, so why does it matter? Your calculator actually gives you an approximation, agreed? For the most time, it does not give you values back in square roots, does it? Nope, it doesn't do that, right? It doesn't work like that. This allows us to keep things exact. Okay, so that's the idea there. The second type of problem that we're going to be taking a look at is what we did back in section 3.1. Okay, so please don't confuse yourself. This 3.2 is not on your gateway. Okay, this is other material. But remember what we were doing in 3.1 was verifying identities. We were taking some expression that looked like this and turning it into some other expression that looked, hopefully in most cases it was a simpler side of the equation, right? So we're going to be doing the same thing here. We're going to be verifying or establishing identities, that one side of the equation can be adjusted to look like the other side. So those are the 2 types of problems we're going to be taking a look at. And we have sine, cosine, tangent. Notice we don't have anything about secant, cosecant, and cotangent. Why don't we need secant, cosecant, and cotangent identities? Okay, opposite. Can you clarify a little bit better, Keith? What do you mean by opposite? Reciprocal. Yeah. So if I were to wanting to do the same thing here for, let's say, cosecant, I could simply lean into which identities here? The sine identities, right? I could lean into the sine identities, I could find what I need to do, and then I could do the reciprocal. Okay, so I don't need a whole bunch of identities that are established for the other three trig functions. I get them because of the fact that I know that they have reciprocals. Okay, does that make sense for everybody? It's also probably worth noting that tangent, you know, is sine over cosine. Nod your head if you knew that. Okay, that's good. So in some sense, yes, there's these tangent identities, but sometimes they're not the identities that are most helpful to use. Sometimes it's easier to use the sine and the cosine identities and to find their ratio to find something for tangent. So we have multiple options, different ways of doing things. So let's take a look at how one type of these problems might set up. So on this one, it's actually set up very nice. And what I mean by that is that they have identified for you that the angle is the subtraction of two separate angles, right? They've told you that the cosine that you're taking the angle measure of is 2 pi over 3 minus pi over 6. Now, we're not going to see that every time. I can't remember if I have an example. Yeah, I do have an example. So when we get in the next page, you're going to see an example where it's not set up quite like that, okay? But this one, introductory, right, we're going to ease our way into it. We see two different angles. So taking a look at your cosine sine and your sum difference identities right here. This one says I've got the cosine of two angles subtracted. Do you see which one that is in your paper? Yep. Okay. So we're going to use that identity to rewrite this expression. So we're going to change this to say I've got the cosine of what angle? What will it start out as? 2 pi over 3. It's the alpha angle, the first one. And it says it's supposed to be multiplied by the cosine of what? Pi over 6, the other angle. What sign comes next? Does it say addition or subtraction? It says addition, so we're going to do addition, right? So as we're taking a look at it, we should be looking at this particular identity. Are we looking at this one? Okay, good deal. It's formatted a little bit differently on your paper versus my screen, but this is the identity we should be looking at. So it is addition. And I've got the sine of those two same angles, right? So I'm going to do sine of the 2 pi over 3 and the cosine, the sine, get the other one, of the pi over 6. Did I get it written in there okay? All looks good? Okay, here's the kicker. Everything on the right-hand side you know how to do. It's from your unit circle, right? 2 pi over 3 and pi over 6 are unit circle values. And sine and cosine are the friendly ones because they're actually either the x or the y value. I don't have to do ratios like I would with tangent or anything with secant or cosecant. So what is the cosine? I want you to think with your unit circle now. Pause for a sec. What is the cosine value at 2 pi over 3? Negative 1/2. Good job, Brady. Okay. Okay, now that you know the answer, because Brady gave it to us, pause for a second. Do you agree? Can you picture it? Okay, good. Okay, pi over 6, we're back in quadrant 1. That one's much more sort of accessible immediately. So what is the cosine value at pi over 6? That's square root 3 over 2. So this is multiplication. We have negative 1/2 times square root 3 over 2 of addition. Okay, now back over there to the 2 pi over 3 value. What is the sine of 2 pi over 3? That one's square root of 3 over 2. And what is the sine of pi over 6? 1/2. Now you may notice what happens immediately right now, but if you don't and you simplify a little bit, you will. So the first one becomes negative square root 3 over 4. And the second one becomes positive square root 3 over 4. And what did you get? This is 0, right? Now how could you check to make sure that the cosine of 2 pi over 3 minus pi over 6 really is 0 if you wanted verification? What could you do? Don't overthink this. You can put it in your calculator, of course, right? You can put it in your calculator. In fact, if you try to do the 2 pi over 3 and the pi over 6, somebody just tell me what that angle measure actually is, because this is not a good example of one where we absolutely needed to do it this way. What is 2 pi over 3 and pi over 6? What is it? It is pi over 2. What is the cosine of pi over 2? 0. It's 0. Okay, now most of the ones we work with are not going to have an angle over here that we know. Like, that's the point. But I wanted to show you one so that you could see that it's verifying something that you know in a different way. Are we good? Okay, so we have to separate them apart. We have to find their individual sine or cosine values. We find those quantities, and then we multiply, and then we add or subtract, depending on what we're working with. Okay, let's try another one. This one, I've tried to put in directions that look a lot like the directions you might see in my math lab. So this is another direction set that you might see. And it gives a lot of pieces to it, right? A, B, C. It says consider the following to be the right side of the formula for cosine of alpha minus beta. So we just did an alpha minus beta cosine, right? We just did that one. It was that one that's circled here, right? So they're giving me the right-hand side, and I'm going to merge it back to go to the left-hand side. And the reason I would want to do that on this one specifically is notice 50 degrees and 5 degrees are not unit circle values, right? Okay, we're going to be flipping back and forth between degrees and radians still in this section. 50 and 5 are not on my circle, correct? Okay, but if I recognize the format on the right-hand side, and it told me by part A that it would, or part the directions that it would be, it matches one of the forms on the right-hand side of our sum difference formulas. We can change it and we can make an adjustment. So it says to identify alpha and beta in the expression, part A. Part B, write the expression as the cosine of an angle. And then part C, find the exact value of the expression. So let's start with A. What is alpha, the way that this is set up? 50, thank you. And what is beta? 5 degrees. So we're going to be good to go in my math lab when I ask this for those, right? Absolutely, for sure. B says that it's going to rewrite this as the cosine of an angle. So this is the cosine of what? If I go backwards, right, from right to left on that sheet of identities. What's it going to be, Sydney? Yep, 50 minus 5. Now, this is actually a really good example of one that I wanted to draw your attention to as well. There's a lot going on in this problem that has commutativity, okay? Addition is commutative. Commutative means I can change the order. So I could put the sines of these values on the first part and the cosines on the second part, correct? Okay, so let's take a look over here though. What I want you to notice, however, is that there are no identities that have the right-hand side that switch the sines and the cosines. So if you had a problem that was written sort of backwards of this one, and it said sine of 50, sine of 5 plus cosine of 50, cosine of 5, if it said it backwards, you should be able to say to yourself, addition is commutative, and if I switch that around, then it looks like that first identity. They could. And there's no reason they shouldn't be able to, because those concepts are concepts that are like well beneath you, but you have to sort of dig back into remembering them, right? The other thing that you notice here that's commutative is that the multiplication is too, right? So this says cosine of 50, cosine of 5. Okay, if you take multiplication and you flip it around, you get the same thing too, right? 3 times 4 is 4 times 3. So in the same fashion, we could actually rewrite this as cosine of 5, cosine of 50, and do the same thing on the other one, right? Now, that would change the identification of our alpha and our beta, right? Our alpha would then be 5, and our beta would then be 50. Why would it not matter? So this one right now, let me write this out. This would say cosine of 45 degrees. But if I did it backwards, right, we'll change colors. Let's say that the alpha is 5 and the beta is 50. So we subtract this in the other order, we'd get cosine of negative 45. Why would that still be okay on this problem?
Because the cosine even and odd identity is something like that.
Yeah, you're exactly right. That's an even-odd identity. Cosine is even. And the cosine of a positive 45 is exactly the same as the cosine of a negative 45. So this is an example of one where the order of the alpha and the beta doesn't even really matter. If it were sine, if this said sine of 45 and sine of negative 45, would it matter? Yes, it would. Why would it matter? It's not even. It's actually odd. And an odd identity actually means that the negative on the inside is equivalent to having a negative on the outside, right? So pay attention to the order. Make sure you identify which one you're working with in the right situation so that you don't get tripped up on those negatives, okay? All right, so we've got cosine of 45 degrees. That's part B. Part C says, find the exact value of the expression. So, what is the cosine of 45 degrees? Square root of 2 over 2. Okay, how could we make sure we're right? You can plug it back into your calculator, right? It is worth noting that if you put the exact expression that they gave you in the calculator, first of all, it's not going to tell you square root 2 over 2, right? That's the whole point. It's going to give you some decimal expression, right? So you're going to have to take that decimal expression and compare it to the decimal you would get by putting in square root 2 over 2 into your calculator. So you can't identify it from just a one-step kind of process. You have to use a little bit of reasoning to make sure that you're identifying the right pieces. Okay, are you guys good? Okay. Just like the 50 and the 5 are not angles on our unit circle, neither are pi over 12 and 5 pi over 12. Correct? Now, this one does not have the directions that this one did, A, B, and C. It doesn't say it in that way. But you kind of got to do it anyway, don't you? You kind of have to identify what are the angle measures. They're pretty straightforward. That's not usually a big deal. But on this one, part B, where it says write the expression as a cosine of an angle, and they told you this is going to be cosine of alpha minus beta, like they told you which one to go to, correct? This one doesn't tell you which one to go to. You have to figure that out. So, taking a look then back at these identities, which one is it that we're going to be using for number 3?
Sine alpha minus beta.
Mm-hmm. It matches this one. Is everybody good with that? Now, that's going to be fabulous as long as when I take the alpha that I'm given and the beta that I'm given and I subtract them, what it is on the left-hand side, it becomes a unit circle value, right? And it will because we've identified the correct one. If you do identify the incorrect one, you might find yourself getting an angle measure that you're going, that's not on my unit circle either, right? That might be a red flag moment to say, whoop, let's just make sure I've got the right angle or the right identity that I'm working with, okay? Red flag. Just because it gave you an angle that's on your unit circle doesn't necessarily mean you picked the right one. But if you get an angle that's not on your unit circle, you know you picked the wrong one. Okay? So we're going to use the one that I've circled in this yellow color. We're going to use sine of alpha minus beta. And let's go back over to number 3. Okay, so I'm going to change this to say sine of alpha, which is pi over 12, minus beta, which is 5 pi over 12. Does it matter that I wrote it as pi over 12 minus 5 pi over 12 versus 5 pi over 12 minus pi over 12?
Yes.
Yes. Why?
Because if you do it this way, like we have on the screen, you get a negative.
Yes.
You get negative pi over 3.
Okay, so Jaden's right. It matters that it's negative, but why does it matter that it's negative? Because over on the other one, it was negative and I didn't care.
Because you have different values on each side, or each quadrant of the unit circle.
I do, but why does it matter for sine if it's negative and cosine it didn't? Because it's odd, yeah. So it's that even oddness that are going around, right? So we've got to make sure that we get the subtraction correct. Sometimes the order matters and sometimes it does, and it depends on the trig function. We're dealing here with sine, the order's going to matter. So what am I going to get when I take pi over 12 minus 5 pi over 12? Okay, so it's negative 4 pi over 12, and then you're right, that would be negative pi over 3. Okay, if you can jump straight to pi over 3, that's cool. If you can't, you need to see that in-between step right down. Now, if you really want, you can think unit circle, negative pi over 3, and you can go with that. It's not a problem. Another option is that, again, you can remember this is an odd identity, right? Not odd as in weird, but odd as in even odd, right? It's odd, which means that this negative can be rewritten in front, and I can put myself back into quadrant 1. And most of us like to live in quadrant 1 a little bit better than we like to live in any other quadrant. Okay? So if we think of it from this perspective, what is the sine value at pi over 3? Somebody said it, square root of 3 over 2. And it's negative because of the negative that we pulled out in front of this value. If you think about it from a quadrant 4 perspective, and you don't pull that negative out, will you get the same thing? Yeah, you absolutely will, because sine is the y value, and in quadrant 4, y values are negative. So you're going to get the same thing either way. It just depends on which of those perspectives you like better. Okay, we have one more of this type of a problem. You ready? Okay, so in all of the cases so far, we were either told what to subtract, or the angles were separated in such a way that we knew that we were subtracting, or we could have added depending on the problems that we're doing. This problem doesn't have that. It just starts out with a weird number, 105. That is not on your unit circle. So your goal at the very beginning of this problem is to figure out, how do I split up 105 to either be the addition or the subtraction of two angles that I do know? That's your goal. So I don't want you to say anything for just a second. Give everybody just a chance to think. And there could be more than one way to do it, and that'd be okay too. What two values either add or subtract to 105 that are helpful? There's lots of values that do it. I want helpful ones. 60 and 45. Those are good ones, right? Those are very nice ones. Not only do they work, but they also both happen to be where? In quadrant 1, which is easier for us to think about, right? It just is. So we can rewrite this over here as the cosine of, and you can put it in either order because addition is commutative, 60 degrees plus 45 degrees. Or you could do 45 degrees plus 60 degrees, right? So we're going to look back at our set of identities, and we're going to look for the one that has the cosine values added together, right? So let me flip over there. Cosine values added together, where am I? We're at the top, you bet. Let me circle it. We're going to be using this one right here in green, right? So we're going to be rewriting it as the cosine of the alpha, cosine of the beta, and then it's minus the sine of alpha, sine of beta. So if cosine of 60, was it cosine next or sine? It was cosine. Cosine of 60, cosine of 45, and then minus sine of 60, sine of 45. Okay, did I get those written in correctly? I think so. All right. Unit circle, cosine 60. What is the cosine of 60 degrees? It is 1/2. What's the cosine of 45 degrees? Square root 2 over 2. Right, good. Okay, now we're going to do sine of the same thing. Sorry, that angle measure was left off. What is the sine of 60 degrees? Square root 3 over 2. And what is the sine of 45 degrees? Square root 2 over 2. Notice this is not going to become 0, but we should have known that, right? Because 105 degrees is not 90 or 180. It's not one of our quadrantal angles. So when we simplify, I get square root 2 over 4 minus square root of 6 over 4. Remember, radicals can be multiplied underneath just like that. And I can join this into a single fraction that's square root 2 minus square root of 6 over 4. That doesn't look anything like any angle value that we have seen yet, right? No trig function of any angle value. We haven't seen that. But that should make sense because we haven't done cosine of 105 before. Okay, do you feel like you have a pretty good feel for the ones that give you values, angle measures involved? Okay, we have two other problems. The two other problems are going to be like we did last time. They're going to be taking an identity and verifying that it works. So remember a few things about verifying identities. First, this is a question mark. It's a question mark that you're told is true. Okay, you're told that this is true. The reason I tell you that there's a question mark is because it doesn't mean that you cannot do something to both sides of an equation, because that utilizes the idea that the equation is already true, and that's what you're trying to prove, right? It's kind of like when people try to define a word and they use the word within its definition. Does that drive anybody else nuts as much as it does me? You can't define a word by using the word in the definition. That's ridiculous. I can't use properties of equations to prove an equation is true when I haven't established it is already. That's the whole point. So what that means is that we're going to work with the sides independently, and we typically start with the more complicated side. And which of the two sides here is more complicated? The left-hand side. I mean, the right-hand side, there's nothing I could even do to change it in a way that would make it nicer looking. It's already pretty nice. So this left-hand side says sine of pi minus theta. This should look like the subtraction of two angles, right? Okay, so let's take a look back at our identities. Subtraction of two angles inside of sine. Whoops, try again. Let's see, that looks like the one that I've got in yellow right here. Is that right? Yep. Okay, so this says that I should be able to separate it with the angle measures to say sine, cosine, and then subtract, and then cosine, sine. That's what I'm going to be able to do. So we're going to apply that to this problem. So working only with the left-hand side, we're going to change this so that it's sine of pi, cosine of theta, because those are the two angles, and then minus cosine of pi, sine of theta. Okay, and I'm only working with the left-hand side. The right-hand side is staying stationary. This is just the left-hand side. But pi is an angle that I'm familiar with. What is the sine of pi? It is 0. What is the cosine of pi? It is 1. What is 0 times cosine? It is 0. And 1 times sine is sine. I have negative sine of theta. Was it addition? Did I write it wrong? Oh, I actually took something you guys gave me wrong. Does anybody know what the mistake is? Let's just pause for a second. I got at the end, it's negative sine. It shouldn't be that. What mistake did I make? The one should have been negative 1. Yep. This was actually negative 1. The cosine pi is actually negative 1, not positive 1. So we can go back, we can fix it, and now we've got it done. Okay, you're going to make mistakes as you do these, just like that. Go back and figure out what the mistake is, fix it, because you knew the process you were doing was generally speaking right, correct? We fixed it, we're good to go. Any questions on that one? Okay, let's try another one. My goodness, we haven't dealt with tangent at all, so it seems like we should. What a mess. Do you agree? This looks awful. It looks very messy. Which side do you think may be the more complicated one to work with? The right side, the tangent side. Yeah, I think so too. And not only that, it's helpful because I know how to write tangent in another way very quickly. Yes, sir?
Could we just switch it to like the sine over cosine properties of tangent?
Yes. Yeah, this is what I think you're asking me, Isaac, is can we change tangent theta or alpha to sine of alpha over cosine of alpha? Is that what you're asking me? Yes, that is exactly the approach that we're going to take. Now, it's going to look messier before it looks cleaner. That happens a lot in life, doesn't it? Whoops. Yep, cosine of beta. I have a mess before I can clean it up. Sine of alpha over sine of... Sorry, that's not sine. Did I get them all written in right? I think they're all there.
Why is it?
It should be addition on top. Thank you for catching that, Camden. I appreciate it. Okay, anything else I wrote wrong? We're good? Fabulous. Okay, how am I going to clean up that? Because we just took something that was messy and made it messier. Any thoughts? There's not a greatest common factor anywhere. There's not something that is identical in every single piece. That's something we could do if it were there, but it's not on this one. Okay, we're going to try a trick. Not really a trick, but a strategy from algebra. We have fractions inside of fractions here. True? Yeah. That's not very pleasant. We're going to get rid of the little fractions, and we're going to do that by multiplying by them. Let me change colors. So we're going to multiply by cosine of alpha, cosine of beta. If we do that, we have to do it to the top and the bottom. Notice, we're allowed to do this. We're not multiplying both sides of the equation, This right here, what we're doing is we're multiplying by the number 1, correct? Yeah, that's what we're doing. We have to apply this to every single one of the 4 pieces that we have. But in doing so, one of the denominators, or the denominator, cancels in every one of them. So on the first one, I do not have the cosine alpha denominator anymore. I have the sine of alpha. The cosine of alpha canceled, which means I'm left with, that shouldn't look like a minus. I don't know why it does. Okay, it doesn't want to erase. Let's try it this way. There we go. Better. It should like multiplication. So the cosine of alpha cancels, but the cosine of beta does not. Okay, but there's no cosine of alpha denominator. This is the same piece. This piece right here became this piece right here. Okay, did everybody see that okay? Okay, we're going to do the same thing for the second one. The sine of beta remains. The cosine of beta denominator cancels, but the cosine of alpha will still be there. Same thing's going to happen on bottom. I have sine of alpha. That's still going to be there. But the cosine of alpha is going to cancel, and the cosine of beta will remain. And I have subtraction. The final fraction is still got a sine of beta. The cosine of beta denominator cancels. The cosine of alpha denominator remains. Now, another way to write this, if you're having a difficult time going with all the pieces, is to simply write cosine of alpha, cosine of beta beside each term. And physically do the cancellations and say, oh, look, here's cosine of alpha and cosine of alpha. And here's cosine of beta and cosine of beta, right? You can cancel them out piece by piece if that's helpful to see. This one and this one, this one and this one, and you have the pieces left. Now that's a disaster of a screen, so sorry about that. But we're down here now anyway. This numerator is over here. Which one is sine of alpha cosine beta plus sine of beta cosine alpha? It is sine of alpha plus beta. So we actually have down here now sine of alpha plus beta. And what is the sine of alpha cosine beta minus sine of beta cosine alpha? That is sine of alpha minus beta. It's the one that's circled in yellow. And what happened? We verified it. It's exactly what I wanted it to be on the left-hand side. So remember, verifying identities has this sort of built-in process that you know the answer when you're done. You know when you're done. It will look like the other side. You verified it. You got it to a place where it identically matched the other side by using legal moves. You didn't just manipulate something illegally, right? Like that's not what you did. You got where you needed to with legal moves.